Hello everyone, this is Dr. Ralm Ricarte here, and in this video we're going to begin Chapter 10, which deals with balances, both material and energy balances on transient processes. And so this video here is going to serve as an introduction to the chapter. What I'm going to start with first in this video is I'm just going to write the general material balance equation that you've written or learned about so far in both MEB 1 and in MEB 2. So the general material balance equation we used in both MEB 1 and 2 has this form, where accumulation is equal to your input minus your output plus any generation or consumption. And so, with this general material balance equation in both MEB 1 and so far in MEB 2, we've just treated it just like an algebraic equation, where each of the letters here, A, I, O, G, and C, we just treated those like constants, right? So I'll write here, we treated the general balance equation like an algebraic equation. Okay? And there's nothing wrong with doing that. It's treating the general balance equation like an algebraic equation is completely appropriate if you're dealing with processes that are operating at a steady state, or even if you're working with a closed batch sort of process and you're only concerned about the states of the process at the final time or at the initial time. Okay? So I'll put useful for understanding steady state processes or the beginning and end of a process. Okay, and so that's what you could do if you treat the general material balance equation as an algebraic equation. Now what we're going to do here in Chapter 10 is we're going to add a little bit of complexity. And we're going to start treating our material balances, and even our energy balances as well, we're going to start treating them like differential equations. Differential equation. And so what that means is that our accumulation term now, our A here, it's not going to be a constant anymore. What we're going to say is it's going to have this form, where Y here is some variable that changes over time, whether it's mass, volume, concentration, or temperature. Okay? And by treating our material balance equations and energy balance equations like differential equations, this is going to allow us to track our processes, to track the transient behavior of our processes. So we'll not only be able to study how they behave at the beginning and at the end, but we could study them at any time that we want. Track the transient behavior of a process. Alright, to show you an example of how tracking the transient behavior of a process would be useful, I'm going to tell you a short story. And the story is going to center around a scientist named Mario Molina. And what Mario Molina did is he developed a transient model, so a model that tracks the concentration of something over time. And what he was tracking was the concentration of chlorofluorocarbons in our atmosphere. So chlorofluorocarbons, otherwise known as CFCs. You may have heard this term before, and that's because what his transient model showed is that these chlorofluorocarbons were actually destroying the ozone layer of the Earth. To tell you this story, I'm going to jump to my other slides here. Alright? And so the picture on the left here is a photo of Mario Molina back in 2005. And the photo on the right here is also of Mario Molina, but this was taken in about 1972 when he was a postdoctoral scientist. Now, even though Mario Molina, what I'm talking about here is atmospheric chemistry, Mario Molina's training or his background is actually in chemical engineering. He earned his bachelor's degree in chemical engineering from the National Autonomous University of Mexico in 1965, and he earned his PhD in physical chemistry in 1972. And after that, he started working as a postdoctoral scientist, where he led research into the behavior of chlorofluorocarbons, or CFCs. Now, at the time, back in the early 70s, CFCs were thought to be some sort of super chemical. They were fairly thermally stable, and at the time, they were thought to be non-reactive and also non-toxic. And for these reasons, CFCs were used in a wide variety of applications and products. They were used in as refrigerants and heat exchangers. They were used in aerosol spray cans, things like hairspray and spray-on deodorant. And they were also used in a lot of biomedical applications as well. Okay? And once again, the reason for that is because they were thought to be fairly non-reactive. And that's true for CFCs that are, on the surface of the Earth. But once these CFCs are, sprayed out of a can and are in the air, they start to diffuse, and they can diffuse all the way up to the stratosphere, hundreds or tens of miles above the surface of the Earth. And it's here in the stratosphere that these CFCs, they're not inert anymore, and they start to react. And they react with the ozone that's in the stratosphere. Okay? And so to explain this, I'm going to jump down here. And what you see here is a little diagram of the mechanism of how these CFCs react with ozone. As you may remember from your chemistry classes, ozone is the O3 molecule, and normally it's fairly unstable. But in the stratosphere, its concentration is pretty steady, it's pretty constant. And that's because ozone is created when oxygen gas, O2, is exposed to UV radiation from the sun. Okay? And so that leads to a constant concentration of O3 gas. And this O3 gas is important because it also absorbs UV radiation, protects us people here on Earth from harmful UV radiation from the sun, and also helps maintain the temperature of the Earth, and that helps maintain the biological processes that are happening here on the Earth. But once these CFCs start diffusing into the stratosphere, they can react with the ozone gas. And so what happens is that, as you can see here, when these CFCs, which I'll circle here in red, when they enter the stratosphere, they could also react with UV radiation. And this causes them, the chlorine molecule, or chlorine atoms off the CFC, to fall off and to form a chlorine radical that you see here. These chlorine radicals can then react with the ozone molecules in the stratosphere to form O2 gas and also a chlorine oxide radical as well. These chlorine oxide radicals can then further react with various oxygen radicals that are in the stratosphere to form more oxygen gas, and more importantly, it helps reform this chlorine radical. And so there ends up being, once these chlorine radicals are released or form in the stratosphere, they basically just stay there forever. Okay? And so what happens here is the chlorine radicals are concentration just keeps increasing, but at the same time the ozone concentration just continuously decreases. And so we start losing the ozone in our stratosphere, and more UV radiation can start hitting the Earth, and that leads to a change in our Earth's temperature, all right, which is bad for all the biological processes that are happening. And so Mario Molina, he demonstrated that this was happening to Earth, not only through experimental measurements, but he also showed that this was happening based on a transient model that he developed, something that showed the kinetics of this ozone degradation reaction. And so what you see here on the right-hand side is a plot where the y-axis is the CFC concentration in our stratosphere, and the x-axis is the year. And you could see that before 1990, so right here, you could see that CFC concentration was just continuously increasing. And as a result, that led to a continuous decrease of the ozone concentration in our stratosphere. And so by developing this model, Mario Molina helped convince, took a while, but he helped convince scientists and policymakers around the world that these CFC products were actually harming our environment. And this eventually led to policy changes that outright banned the use of these CFC products. And so for his work, Mario Molina was actually awarded the Nobel Prize in Chemistry in 1995. And so as you can see, the ability to track the transient behavior of a process is critically important. And so what we're going to do here in this chapter is what you're going to learn in this chapter is you're going to learn how to manipulate these differential equations, these differential forms of the material and energy balance. So manipulate differential material and energy balances, and you'll learn how to use them in order to derive transient models that help you track things like concentration or even the temperature of a process.